Good afternoon, everyone. It's a great pleasure to be here. Let's switch for a moment to foundations of quantum mechanics. I will be talking about some polygamous aspects of quantum non-locality. The work was done in collaboration with people from Munich, Debrecen, and our local team from Gdansk. Let me start by explanation the concept of monogamy and polygamy, how we define them. In the famous scheme by Toner and Verstraete, we have three observers sharing 3-qubit quantum states, and the observer A tries to violate the CHSH inequality together with the observer B and C simultaneously at the same time. And it turns out to be impossible. If you look at this graph, on the axis you see the values of the CHSH expressions, AB and AC. And we know that both of them classically are limited by 2, what means that all classical strategies are inside this green square. On the other side, the maximal quantum value in this system is represented by the red circle. And the circle can be recovered by the following quantum states and measurements. And of course, each inequality can be maximally violated with the maximal quantum value of square root of 2 separately. However, if one inequality is violated, then the other cannot be. This is what we call monogamy. And we claim that such a strong monogamy relation works only for 3 particles. How we generalize this scheme for n qubits? In order to demonstrate the polygamous nature of quantum non-locality, we consider 2 settings, Bell inequalities, involving n-1 particles in all possible configuration. For example, for n equal to 4, we have 4 observers, A, B, C, and D. Each of them performs 2 alternative measurements, A1 and 2, and so on. And we consider all possible tripartite subsets, ABC, ABD, ACD, and BCD. And our question is it possible to find such Bell-type inequalities, ABC, and so on, that all of them are violated at the same time? At the same time, it means in the same setup and by the same n-qubit quantum state. How to find such inequalities? We make the problem symmetric. We assume that the quantum state is permutationally invariant. It means it should be expressed as a superposition of the decay states. And the second assumption, we assume that observers measure the same pairs of observables. The first measurement setting is the same for Alice, Bob, and so on, and similarly for the second setting. And now the problem is significantly simplified. Our task is now to find an n-1 partite Bell inequality violated by the n-1 qubit reduced state of this PI state. Due to PI symmetry, if one such inequality is violated, then automatically all n inequalities are violated if we observe polygamy. The first try would be to verify if the well-known Mermin inequalities can be a good candidate for such inequalities. And referring to the last sentence from the previous slide, it is enough to check that n-1 qubit Mermin inequality is violated by the pi state after tracing out one particle. To this end, we know that Mermin operator can be uh, expressed by projectors onto G8Z state, and then in terms of the decay states. It allows us to simply calculate the expectation value of the Mermin operator, which reaches maximum equal to 2 to the power of n minus 2 divided by square root of n for the following quantum state being a superposition of the decay state, particular decay state, it's actually the W state, and 111 state. And it is interesting that from n equal to 5, the expectation value is greater than the classical bound. It means that from n equal to 5, all Mermin inequalities in all configurations are simultaneously violated. What is more important, the violation grows exponentially with the number of qubits, and it is even maximal in the limit. Okay, what is the situation now? For 3 qubits, we have strict and strong monogamy. From n equal to 5, the polygamy can be revealed by the Mermin inequalities, but what with n equal to 4? We know that for n equal to 4, we cannot violate all tripartite Mermin inequalities, but other inequality with this property. Fortunately, or maybe unfortunately, I don't know, there is a positive answer. And using linear programming method, we found such inequality for the partition ABC and similarly for other three partitions. If you are interested in it, you can find here the description, detailed description of the method and the Mathematica code to generate Bell inequalities. And the found inequalities, all of them are violated maximally by the following state, which looks familiar. It is again some particular superposition of the W state and 111. So even for 4 qubits, for n equal to 4, there is no any fundamental reason why all tripartite Bell inequalities cannot be violated. So the strong monogamy rules does not apply here as well. We have experimentally demonstrated the polygamous Bell type correlation using 6 photon decay state prepared by experimental group from Munich. And what is interesting here, if we trace out one particle from the decay state, we end up with an equal mixture of 2 decay states. And the state has the very strange property that it does not contain 5 qubit correlations, which are necessary to violate 5 qubit Mermin inequality. Okay, because 5 qubit Mermin inequality is expressed in terms of 5 qubit correlators only. But we can use again our linear programming method to find another type of Bell inequality, which has the following form, and similarly for all other 5 partitions, which for optimal settings in XZ plane is violated in any 5 partition. Okay, the classical bound is 6, and as you can see, the violation is always above 6. And here in the picture, you can see how the violation of this inequality depends on measurement settings. In the ideal theoretical case, the region where we observe polygamy is colored. Due to some experimental imperfection, the region is a little bit smaller, but still significant. Okay, this is my last slide, conclusions. We demonstrate that Bell violation is a true polygamous phenomenon, at least for number of particles greater than 3. And in such a case, quantum non-locality can be shared among arbitrarily many particles and not be concentrated only on a particular level. That's all. Thank you for your attention.
Thank you so much. Yeah, let's applause. Okay, it was a nice talk. Do we have any questions from the audience? Okay, still thinking. How does
Maybe not so nice.
No, people are rethinking once again. So how does this fact that Bell inequality violations aren't always monogamous impact the security of, let's say, quantum cryptography?
Yes, it's a very good question. Of course, we can use this advantage of monogamy or polygamy in all tasks that take advantage of standard non-locality. Okay, like you said, quantum security of quantum key distribution or computational complexity and so on, and the monogamy of Bell inequalities for quantum key distributions guarantee that the other observer, which is eavesdropper, for example, has no access to our channel. Okay, polygamy. I think it's quite different perspective. For example, we can use polygamy to distribute our security between many different configurations, many different subsystems. Okay, so it means that we have many secured channels at the same time.
So it sounds as a good thing.
But yeah, this is kind of trade-off relation. The security is a little bit lower. Okay.
Okay, do we have any more questions? Okay, so maybe later. Let's thank again our speaker.
Okay, thank you.